how am I going to do it using U-substitution? What am I going to let U equal?
I would do x squared plus 1.
Okay. Now, the whole point of U-substitution is to turn this thing into an integral of U with a du, because you cannot integrate a function of U if it's dx. So you have to turn everything we see there into some form of U. And let's watch how we do it. The first step is always to differentiate the U. What is du dx equal to?
It would be 2x.
Which makes du equal 2x dx. And I'm going to do it perhaps a slightly different way, just for explanation purposes. You with every step of that?
Yep.
Okay, so now I'm ready to substitute. Okay, I still got my 2x. Well, I got the square root of u, or let's make that u to the 1/2. And in place of dx, I'm going to put du over 2x. Notice that the derivative of u always ends up in this denominator. And it cancels out that 2x. And now I have something that I know how to integrate. How do I integrate this? What's the integral of u to the 1/2?
It would be u to the 3/2 over 3/2, which is basically just 2u and over 3.
Okay, and then I go back, and for u, I substitute x squared plus 1, and I have my answer.
Yep.
Okay, this form of u substitution is the form of f of g of x, a composite function. That's what this was, times g prime of x. That's what this was. So whenever you see this, they call it pattern recognition. You kind of look for it when you're looking for ways to do integration. If you see a composite function where the derivative of what you would let u be is in the numerator, then it's going to take care of this 2x. And I'm going to have a nice simple function of u without any x's in it. Okay, this is the classic form of u substitution. Now, what would happen if I didn't have that 2 there? Well, now when I get to this step here, I'm going to have a 2 in the bottom. But remember, when you have integrals, you can always factor out constants. So there's a couple of ways to handle that. You could just cancel the x's out and then integrate u to the 1/2 over 2. But a technique that they kind of like to use is to multiply the inside by 2 and then take a 1/2 out there. I can always do that. I can multiply the inside by 5 and take a 1/5 outside, because that 1/2 times that 2 is 1. So I can always do this kind of a technique. And then I've got the exact numerator that cancels with that denominator, and I know how to integrate whatever's left.
All right.
Last week, the problem we had ended up coming down to sine cosine. It was a very complicated, it was a ridiculous problem to teach somebody U-substitution. But nonetheless, if I have sine x cosine of x, notice that I can use the power rule. I'm going to let u equal sine x, which means du dx equals cosine x, which means du equals cosine x dx. And this time I'm going to take a little bit of a shortcut. Instead of solving for dx and letting it equal to du divided by cosine x, I'm going to search the integral and see if I can find that. And I'm looking at it right there. So I can substitute du for that. So now the integral becomes sine x, which is u. The rest of it is du. Well, that's easy to integrate. And notice that this problem is the exact same format. It's not a composite function, but it's a function with the derivative next to it. And that's the key. In other words, I could actually integrate any number you want to put there. As long as I've got cosine x next to it, then u is going to be sine x, and I'm going to end up with u to the fifth. And I know how to integrate that. All right. Okay. One other type of U-substitution. It's called change of variable. And it's how you would integrate something like this. Notice that I don't know how to integrate that. Right? In other words, it doesn't fit the classical U-substitution of the previous problem. We don't have the derivative of the bottom on the top or anything. But let's just see what happens if, here's the problem with this. If I had this, it would be no problem at all, because that turns into 1 plus 1 over x. I can now integrate both pieces. When I have x over x plus 1, I cannot separate that into two fractions. That is not that plus that. That's not a legitimate algebraic thing you can do. So right off the get-go, we have a problem with how to solve this. But if we can turn it into where the denominator is a single thing, then we'll be in good shape. So here, I'm going to let u equal x plus 1. What's du dx?
Just 1.
So du is equal to dx. Furthermore, now this is a little different. We have to actually solve for x. X equals u minus 1. Just doing algebra on that. So we can go into this problem. X is u minus 1. X plus 1 is u. And dx is du. Now I know how to integrate that. I don't know how to integrate that, but this I can turn into two fractions. In other words, because my denominator is a single entity, this thing is the same as u over u du plus the integral of 1 over u du, which is the integral of 1, which is u, plus natural log of u. What was u? U was x plus 1, so we have x plus 1 plus natural log of x plus 1 plus c. Completely different style as to how the U-substitution worked, but those are the main two, in fact, I believe the only two methods of U-substitution. And one is basically referred to as pattern recognition, where we're looking for a composite function times its derivative of the inside. So we can use U-substitution whenever we see something like that, where u is gx. Or change in variable, where you do something that is on the order of this problem down here. And you'll notice completely different. It's not the same pattern. It's not pattern recognition. but U-substitution works on it, as long as you solve for x. The key to remember is that you cannot integrate, you have to have the same variable. Whatever your variable of integration is, in this case it's dx, then you need all x's. Or if you're going to change it to du, you need all u's. If I had this and I had an x out here like that, I couldn't integrate it.
Okay.
You can't integrate by du when there's an x in the function. Everything has to be u's. All right. Now, U-substitution is pretty complicated, enough that I would think that you would have been on it all week.
Yeah, we did a lot of U-substitution. Now we've kind of moved on to definite integration with like a number at the bottom and a number at the top of the integral sign.
Yeah, all of these are indefinite, where there's no limits of integration.
And we had a quiz on indefinite integration, which is like called Integration Quiz 1 or Integral Quick Quiz 1. And I did all right on it. It was just like 30 questions, and I missed like around 5. So
good.
I think the grade on it wasn't great. It was like a 66%, but out of like the number that there were, I only missed a couple. But so I'm feeling fairly confident on the indefinite. And then when she threw in the definite in the lesson.
Well, the definite actually just makes it easier. I mean, it doesn't make it harder at all. If I'm integrating that, that's x cubed over 3 evaluated from 2 to 3. And there's no c when you do definite integration.
Yeah, right.
Okay. So everything I talked about for U-substitution, you understood? You already understood it?
Yeah. It made more sense, especially that last one with the x over x plus 1.
That's a little tricky. Yeah. If you're good at U-substitution of the classical format, then that second one tends to throw people a little bit.
Yeah.
But the trick is to get the u as a single denominator instead of what we had, which was x plus 1 as a denominator.
Yeah.
That's how I knew to let u equal x plus 1, because then I'm going to end up with u in the denominator.
Yeah. Right. So.
All right. Do you have that quiz? Did they give it back to you?
No, she lets us see him in class, but she doesn't let us take it home or anything like that. But there is a few questions from like the WebAssign homework that I have.
Okay.
Some of them a little confusing.
Can you verbalize
it? It's a little yeah.
Okay.
I probably can. So it says you are given the following, and it's the integral, and then the top number is a 0 and the bottom one's a -3. And then it says g of t dt equals square root of 2. And then there's
the integral is equal to square root of 2.
Yes.
Okay.
And so then it has 4 questions under that saying to find each integral.
Okay.
Yeah.
What are they?
The first one is the integral with -3 at the top, 0 at the bottom, and then it just says g of t dt, which I think like the rule is you just switch it around, right?
Just add, it becomes a negative. In other words, this becomes negative square root of 2.
Okay.
Whatever it is in one direction, if you reverse the limits of integration, it just changes the sign. Had this been negative square root of 2, this would be positive square root of 2.
Okay.
Okay.
All right, so I got that one, and then the next one is it's the integral with 0 at the top and -3 at the bottom, and it says g of u du. which is a little confusing, but
And they want to know what that's equal to?
yeah. Because I don't really know where you get the U.
I don't either.
First place. This is a maybe.
If I had to guess, I would guess square root of 2. But they don't give you any other information as to how t relates to u?
Yeah, that was it. Which I don't really. This one doesn't really make a whole lot of sense.
Let's see what happens here. If I take the antiderivative of that, evaluated at 0, minus the antiderivative evaluated at minus 3. That's the fundamental theorem of calculus. In other words, the way we handle definite integrals is by finding the antiderivative of the function evaluated at the top, subtract the antiderivative of the function evaluated at the bottom. So that's what was equal to square root of 2. Now, down here, it's still going to be g of 0 minus g of minus 3. Question is the antiderivative of g of u? I don't know. I'm a little confused. It feels like we're missing some information.
Yeah, I just tried square root of 2 and it was right. I think it was just tricking us up with like they switched around the letters just kind of.
Okay. So,
but,
yeah, square root of 2, like I said, that would have been my guess.
Yeah.
What else?
That was kind of dumb. Okay, so this one says evaluate the integral, and then it's 2, or the integral, and then 3 at the top, 0 at the bottom, and it says 2 dx over x plus 1.
2 dx over x plus 1?
Yep.
Okay. Probably the easiest way to handle when you have a number is to take it out. Okay? In other words, take it outside of the integral, that 2. I can definitely do this. You can take constants out. You cannot take variables out. In other words, I can't take an x out if I had one to take out. I couldn't do it. Okay? Only constants. Now, what is the integral of 1 over x plus 1? Or what is the antiderivative of it?
Should you bring it up and do x plus 1 to the minus 1?
Okay, I'm just going to do that as an exercise just to show you why that won't work. But it might ring off some bells as to what the antiderivative of 1 over x plus 1 is. Okay, so what are you going to do here?
Oh, well,
use the power rule?
You can only use power rule if it's just x, and there's a plus 1 in there, so I see why that wouldn't.
Well, here's what was happen is I would add 1 to the and then divide by the new. So I would end up with x plus 1 to the 0 power divided by 0. 1 divided by 0 you can't do. So the only integral you cannot use the power rule on is when the exponent is minus 1. And there's a very special function that is the antiderivative of that. Natural log of x plus 1.
Okay.
Notice that if you were to have a function, y equal natural log of x plus 1, and you wanted y prime, it'd be the derivative of the outside, which is 1 over x plus 1, times the derivative of the inside, but that's 1. So we don't have to multiply by it. So whenever you have an expression like this, the integral is always the natural log of that function. And there is a 2 outside still, and we are evaluating it from 0 to 3. So that would be what? How do I evaluate that from 0 to 3?
So which is like in general, when you get to this point, is it like you plug in the bottom and subtract it from the top, or do
The
you
other way around. Always start with the top.
Okay, so plug in the top, then subtract it from the bottom.
Well, no, then subtract the bottom. So I'm going to have the natural log of 3 plus 1 minus 2 times the natural log of 0 plus 1. Okay? And I can factor the 2 out, but I don't really need to factor anything out. What's the natural log of 1 going to be?
0, right?
Correct. So this whole term disappears, and my answer is 2 natural log of 3 plus 1, 4 rather, and that's a number. Or I could even convert it to natural log of 4 squared, 16. There's your answer.
Okay, cool. All right, that works.
And that's why natural log is such a huge function for calculus, is because whenever you're integrating anything that looks like this, that's natural log of 2x plus 1 divided by 2, or multiplied by 2. I might have to go through the math. You would have to let u, in other words, I'm going to use U-Substitution. If I had this problem right here, okay, u is going to be 2x plus 1, du is going to be 2 dx, so I have an integral of 1 over u. In place of dx, I got du divided by 2. I take that 2 out there. Now I can do the integral. In other words, that is going to become 1/2 natural log of u. But u is 2x plus 1.
Okay, that makes sense. So,
And the harder or the more deep you go into calculus, it turns out you have all of these different techniques. There's at least 5 more techniques that are just as hard to understand as U-substitution. But a lot of them will start with a complicated function and end up with something that looks like this, plus something that looks like this, plus something that looks like this. And so you end up with your answer being 1/3 natural log of 3x plus 1 plus natural log of x plus natural log of whatever's in the denominator over there. And you haven't gotten to integration by parts yet?
oh, where you split it up? Yeah, we have. We just kind of touched on it. We haven't really gone over it much, though.
That's a toughie. That's probably tougher to understand than integration by substitution. It's basically the product rule in reverse. Okay, you notice how when we had u times v, when we differentiate that, it's uv prime plus u prime v. Okay, pretty easy. Well, if you have the integral of uv du, that's kind of like the product rule. In other words, if you have the product of one function times another function, and these could be anything, these could be e to the x, sine x, whatever, but if you have the product, here's what it's equal to. uv minus the integral of voodoo, v du. Now, right off the get-go, it looks like we haven't done anything. In other words, we didn't know how to integrate that, and as all I did was turn it into uv minus something else. Well, if you choose your u and v properly, you will be able to integrate this second part. Shall we go through an example? Well, we got 3 minutes. I can do a quick example in 3 minutes.
Okay.
Take a real simple one. X e to the x dx. Now, there's something called log poet. Or lipid, actually, I like better. Have you heard either of those words?
I am not.
This is an acronym that allows you to figure out what to make U. Okay? If there's log in the expression, make U that. If there's inverse trig functions, make U that. If it's a polynomial, make U that. If it's an exponential, make U that. If it's a trig function, make U that. In that order. Okay? So, what I'm going to let U equal to is polynomial, because I'm faced with a polynomial times an exponential function. So U is going to be X, and everything else is dx. In other words, E, or dv rather. dv equals everything else, which is e to the x times dx. Now, here's where it gets a little tricky. I always write it like this, where I write the u on the left and the dv on the right. Those are the two things I need to understand, what u is going to be and what dv is going to be. Okay, and I'll show you why real quick. Du is clearly equal to dx, and over here on the right side we integrate. In other words, it's really, this means dv dx equals e to the x. Well, that means that v equals e to the x. Okay? And remember what this whole thing was equal to. uv minus the integral of v du. Well, do I know what u is? That's what u is. Do I know what v is? That's what v is. Can I integrate the integral of e to the x dx? Yes, it's e to the x. So my answer becomes the integral of x e to the x dx is equal to u, which is x, times v, which is e to the x, minus the integral of e to the x dx. And this I can integrate. It's equal to e to the x. There's my answer. Now, when you're doing integration by parts, it usually makes sense to factor out if you can. And I can factor out an e to the x, and I'm left with x minus 1. So this would be plus c. That would be the answer to that indefinite integral. And the trick always is to figure out what to make u. There are some problems where the trick is to figure out what to make dv, but that's what you have to figure out with integration by parts, is what to make u and what to make dv. And lipid is what you use to figure out what to make u. Everything else is dv. And then you differentiate on the left, you integrate on the right to get to where you know each of those 4 variables. In other words, you need to know what u is, you need to know what v is, and you don't get v until you integrate that. And then you need to be able to take this integral right there. So you need to know what du is. And some of these are so hard that if I had an x to the 6th, the first iteration would leave me with x to the 5th e to the x. I'd have to do it again, knock it down to x to the 4th. I'd have to make 6 iterations to solve that problem. That's how hard integration is.
Yeah, that would that'd be rough.
Well, by heart. I mean, it's not hard to make multiple iterations. They actually give you a little routine for doing that. But the fact is that with the first iteration, you can't always do this integral, the integral of v du. But it gets closer and closer to being doable as you do each iteration. The problem with these kind of problems is you end up with a string. You know, if you have to do this again, then you got a uv minus an integral of whatever's next. So you end up with this giant long expression that has about 10 negative signs in it. And you have to be very, very careful that you don't lose a negative sign.
Right.
And that's the hardest part about this. The method of doing integration by parts is relatively straightforward, especially if they teach you lipit. If they don't teach you lipit, it becomes rather tough because we need a rule to tell us what we're going to let u be. You know, for this problem here, u would be x to the sixth because polynomial comes ahead of exponential. If I had an x to the sixth natural log of x, then u would be natural log of x, dv would be x to the sixth dx. Remember, dv is always everything that isn't u.
Okay.
Okay? It's
right.
They may have spent very little time on it in class, but that probably means you're just getting started.
Yeah.
Because this is harder to understand than U-substitution.
Yeah.
I mean, how often do you take an expression like this and break it up into a u and a dv? That's just something we've never done before. So it's definitely a methodology that you need to memorize and then just go with it. Just, in other words, once you've defined u, integrate to determine what du is. And once you've let dv equal something, differentiate on the left, integrate on the right. You need to integrate this in order to solve for v. And you need v.
Okay.
Okay? Just doing a half hour today?
Yes.
Okay. Sounds good.
All right.
I will
Thank you for
let you go with that. Yeah, these are two extremely difficult subjects, integration by U-substitution and by parts. Typically, I would say you would spend a week on each, at least.
Yeah. Yeah, I think there's a lot more to go with in integration. She did spend a decent amount of time on the U-substitution to kind of make sure that she added that in, but I think we have a lot more time to go on the rest of the types of
that
integration.
may be all that you learn in the techniques of integration this year, is U-substitution and by parts. You may learn partial fractions, which is even trickier. Mainly because people haven't done partial fractions in ages. You probably haven't done partial fractions in 4 years, where you take a fraction and split it up into its two partial fractions.
Yeah, I'm thinking.
If you're going to do that, you'll cover that shortly also. But I think those three methods of integration are probably the only three you're going to learn in Calc AB. The other ones you don't get until Calc BC.
Okay.
Okay? All right. Luke, have a good week. I will talk to you at 3 o'clock next Sunday.
All right. Sounds good. Thank you.
All right, bye-bye.